Okay, the objective of this lesson is students will define rotations and the angle of rotation, and we'll be working various examples of those things. Okay, so we'll start with a definition. A rotation moves a figure along a circular path around a center of rotation. So let me see here. Let's see if we can draw this. If I have triangle ABC, A, B, C, and we have a center of rotation, O. I can take each point and connect to the center of rotation, so I'm going to do that with C, and let's say I want to rotate it this much. Well, C prime would be the same distance away from that center of rotation as C is, so there's C prime, and B prime is going to be right along, lined up with C prime, since C and B are lined up. C prime and B prime are going to be lined up. So B prime would be up there. And then A prime is going to be over here. So the whole thing is rotating. Okay, so that represents a rotation in this direction. Here's my pre-image. There's my image. So we can represent rotations clockwise or counterclockwise. Clockwise is, if you follow, clockwise would go around like this, just like the hand of an analog clock. So if I draw it, we usually say CW represents clockwise, and that would be this direction. That's actually considered a negative rotation, so that would be a negative degree, number of degrees when you rotate. Okay. Counterclockwise, CCW. That goes against the clock. It goes around like this. So that would look like this kind of an arrow, and those are our positive rotations, so that's our positive degree measure. And I always remember that by thinking about the coordinate axes in the 4 quadrants. I know it sounds weird, but these are my 4 coordinate axes. 1 is up in the upper right, and then we have 2, and 3, and 4. And this notation is the same for every math class from here on out. The positive angle direction is counterclockwise, and it's going in the order of the quadrant numbers. That's positive. Okay, we also have our notation and some symbols. So if I scoot up here, the symbol theta. So we have a Greek symbol, or a Greek letter, I guess. The symbol that's called theta. It's an oval with a line through it. That is used to represent an angle measure. It represents angle measure. Okay, so you'll see that symbol every now and then. The notation for a rotation is a capital R, and that's important. So a capital R represents rotation. So to represent a rotation, it would be capital R. You'd have some kind of center of rotation and angle. So C is the center of rotation, some point. And theta is the angle that it's rotating through. It can be either positive or negative. Okay, so here's some examples. The first one, just describe. Tell me what's going on when you see these symbols, a capital R with an O and a negative 30. Well, what that would represent is a rotation about point O, because that's my center of rotation. You always have to denote the center of rotation. And that's 30 degrees clockwise. And that's how you represent it. Negative 30 tells me that it's going this way, okay? For the second one down here, we want to write in symbols. A counterclockwise rotation of 120 degrees about P. So it's a rotation, so I use capital R. The center of rotation is P. Counterclockwise is positive, so you just have to write 120. It's that easy, but we do have to know the notation, even though your book doesn't show it much, if at all. Okay, so the next part talks about, we want to talk about the angle of rotation of a figure. A complete rotation is 360 degrees, so if I take any kind of figure, a triangle, a polygon, a square, and I rotate it about its center 360 degrees, it's back to its original position. But symmetrical figures can be rotated less than 360 degrees and still map to themselves. So here's what I said, just written down in words. Again, a symmetrical figure, if you studied symmetry in art, it would be like a regular polygon where all the sides and the angles are the same. You can rotate those less than 360 degrees and it will map to itself again. So, for example, if I have a square, let's see if I can draw a square. If I have a square, I know I can spin it all the way around and it's going to look like itself. But I could even, it won't let me rotate it, let me move it, but I can't rotate it. But I could rotate it just a quarter of the way if I rotated it up here, and it would still look like itself. So mapping to itself, for a figure to map to itself, it means you can rotate it about its center and it would look exactly like the original. So here's how we figure this out. Here's an example. What is the minimum angle of rotation for a regular hexagon to map to itself? So what is the smallest amount of degrees that I need to spin this thing on its center for it to line up and look like the original? A regular hexagon is a six-sided figure. So let me see if I can draw my six-sided figure and make it kind of look like a regular hexagon. If it's a regular hexagon, that means all the sides and all the angles are the same. Well, you got to assume that, let's just pretend that it's a regular hexagon, okay? I have 6 sides and I have 6 angles. I have a center here. So basically, if I know this angle right here and I turn it that much, that's enough for the figure to look like the original. So here's how you do that. It's really easy. You take 360, divide by 6, the number of sides, and every one of those is 60 degrees. So every time I rotate this guy 60 degrees, it's going to map to itself again. The minimum number is 60 degrees, but if you rotated it 120, it would map. If you rotated 180, it would map all the way around, each multiple of 60 until you get to 360. Okay, there are a lot of examples in the book like this. A wheel has 5 spokes, so let me draw that. I'm going to draw a circle, kind of, and I'm going to try to draw 5 spokes here. 1, 2, 3, 4, 5. So in this kind of problem, you're going to assume, even though my picture doesn't look like it, that all 5 spokes are evenly distributed around the wheel. Now this one looks terrible. That one probably should be moved over a little bit, but you just have to, drawing is not to scale. If I have point A, that's here, and point B, that's there, we want to find the angle of rotation to map A to B. Okay, again, we want to determine the angle of rotation. How much do I have to spin this wheel through how many degrees to get A to line up with B? Okay, now granted, at that point B would be down here, but to put A where B is originally. Okay, so we do the same thing. We start with the 360. This time we have 5 spokes. Whoops, I shouldn't talk and write at the same time. Okay, 360 divided by 5. This time it's 72. So each one of these is 72 degrees. Well, looks like it takes 2 of those to get over to B, because I rotate it once, I'm here, I rotate it again, I'm at B. So 2 times 72 is 144. So if you spin that wheel 144 degrees in the positive direction, counterclockwise, A would map to B. Finally, this is another typical example. What is the angle of rotation to map A to E? Let's say, what's the minimum angle of rotation to map A to E? So I could spin it this way, but that takes a lot longer than spinning this way. This is the clockwise direction, so my angle is going to be negative. Okay? We're going to assume this is a regular hexagon. We have 6 angles, so 360 divided by 6 is 60 degrees again, only I need to go this way. So there's negative 60 and another negative 60, so it's negative 120. Okay? And that is basically the types of examples you're going to see with rotations in your homework today.